So these are video notes for section 7.7. We're going to talk today about inverse relations and the inverse functions. And so first we have a relation is a pair of elements. You have the elements in the domain and the range. And the inverse relation, it flips that. So whatever was in your range is now your domain. Whatever was your domain is now your range. So you see that example. Here we just switch the domain and the range. So we can look at these relations, and we're going to compare the range and domain of different relations. So let's practice first finding the inverse. So we're given this relation M in terms of x, y. There's our order pairs. So for the inverse of the relation M, we're going to flip-flop the x and y. So instead of having a point at -1, -2, our new point will be at -2, -1. Instead of 0, -1, it'll be -1, 0. We'll have -1, 1, and -2, 2. So we're just switching up the x and y columns. So whenever we go to graph this, we have a point now at -2, -1, -1, 0, -1, 1, and -2, 2. So here's our graph of the inverse of M. So let's look at just the domain and range of each one. So the domain, again, is the relation of all sets of inputs or x coordinates, and the range is all the y coordinates. So if we look at M, our domain, D, we have the points -1, 0, 1, 2, and for the range, we have -2 and -1, and then those repeat. For our inverse function, for the domain, we have -2 and -1, and for the range, we have -1, 0, 1, 2. So you can see again they have flip-flopped. Okay, we're also going to look at finding this domain and range from a graph. But going back to the graph before, so let me pull mine up here. Is the relation M a function? This could be a function because every element in the domain graphs to exactly one element in the range. So we have each x goes to exactly one y value versus the graph of the inverse of M. We have an x value here at -2 that has two different y values. So this is not going to be a function. Okay, and so just putting this y or y not, the relation M is a function because each x goes to only one y. And here, the inverse of the relation M is not a function because the x value goes to more than one y. We have a point at -2, -1, and a point at -2, 2, which is not allowed in a function. Okay? Another way that you can identify functions is by doing a little chart here where you can draw your arrows from each element in the domain to each element in the range. If it is a function, then each element in the domain should have exactly one arrow coming from it. We can also use the vertical line test, in which if you take your pencil or some sort of vertical line and go horizontally across the graph, your pencil can only be touching one part of the graph at a time. So when we get to here, my pen is touching the graph at 3 different points, so we know it is not a function. However, on this graph, at any given point, my pen is only touching the graph at one spot. So in this case, this graph is a function. Alright, so going back to our original relation M, we had, here's the inverse of M. If we plot those points, what do you notice about the two graphs and this line here, which is the line y equals x, with a slope of 1 going through 0, 0. Well, you should notice that is nicely reflected over the line y equals x. So the graph M and its inverse is just reflected over the line y equals x. And we'll continue to look for this same pattern. Alright, so how do we calculate the inverse of a function? All we're going to do is take our original equation of a line and we're going to switch the x and y, because that's what we do in our table, that's what we're going to do in the equation. So here we have y equals x squared minus 2, so we're going to change it to x equals y squared minus 2. But since we want to see the graphs of these look like, we need to now solve for y. So I need to get y by itself, so I'm going to add 2 to both sides. So I get x plus 2 equals y squared, and I need to square root both sides to get y by itself, which means y equals plus or minus the square root of x plus 2. So this is going to be our new inverse function. Okay? So let's look at example number 3 now. We're going to look at the function f of x equals the square root of 2x plus 2. So first we need to find the domain and the range of f. So let's just, to get an idea, let's make a table. -1, or -2, -1, 0, 1, 2. Good place to start. We can always add more later. And so if we plug those in for x, what do we get for f of x? If we plug in -2, then we get the square root of -4 plus 2, or the square root of -2, which is not possible. So this isn't going to work. If we type in -1, we get the square root of -2 plus 2, or the square root of 0, which is 0. If we type in 0, then we get the square root of 0 plus 2, or the square root of 2. Type in 1, we get the square root of 4, which is 2, and if we type in 2, we get the square root of 6. So we can see that anything that is less than -1 is not going to work, because we're going to be taking the square root of a negative number. So here our domain is going to be all the x values that are greater than or equal to -1. We can't put anything less than -1, because then we get an impossible answer. For our range, let's try the same thing, just to see. For our range here, we don't need this. We're looking at our original chart. So range, we're looking at what values do we get. Well, we know we can't get anything less than 0. If we have something smaller than 0, we're really taking the square root of a negative number, which is not possible. So in this case, our range is going to be all of the y values, or f of x, that is greater than or equal to 0. We're not going to get anything smaller than 0 whenever we're taking the square root. Okay? Alright, now let's find our inverse function. So again, for our inverse function, if this is y equals, we're going to switch our x and y. So we have x equals the square root of 2y plus 2. To get rid of that square root, I want to square both sides. So I get x squared equals 2y plus 2. Get y by itself, I'm going to have 2y equals x squared minus 2. And divide everything by 2. So y equals 1/2 x squared minus 1. So there's our new inverse function. So if we look at the domain and range of our inverse function, let's just make our little table just to see what we notice. And notice every time we write the inverse function, we have it going to the -1 here. Okay, so now we're going to use this inverse function. So if I plug in -2, then I get y equals 1/2 times 4, so that'll be 2 minus 1 is 1. If I plug in -1, I get y equals 1/2 minus 1, or -1/2. If I plug in 0, I get y equals 0 minus 1, or -1. If I plug in 1, I get 1/2 minus 1 is -1/2. And if I plug in 2, I get 4 times a half is 2, minus 1 is 1. So notice this is a quadratic. It's going down to -1 and then coming back up. So our lowest point in our y is going to be at -1, but we can put in any x value here. So my domain is going to be all reals, and my range, the smallest thing my range can be is -1. So my range is going to be all the y's that are greater than or equal to -1. Is this a function? So think about it on a graph. This is going to look like a nice quadratic. Every x is going to exactly 1 y. So yes, this is a function. We can think of, if we graph this, it's going to be a nice quadratic, and it passes the vertical line test. We could also check more points just to make sure that every x does indeed just go to 1y. Okay, so last page. Let's look at the function y equals x squared plus 3. Does this define a function? We're going to say yes. It defines a quadratic function. Okay, we know we can graph that. We're going to put our vertex at 3, and it's going up 1 their side, so it's going to look something like this. Okay, and we know that makes a nice, pretty quadratic function. So what about its inverse? Is its inverse a function? Well, in order to test that, we need to find our inverse. So I'm going to flip my x and y. So I get x equals y squared plus 3. I want to get y by itself, so I move that 3 over. X minus 3 equals y squared. Square root both sides, and I get y equals the square root of x minus 3, which could be plus or minus. But again, when we plug in numbers here, we're just going to only take the principal root and assume it's positive. So let's see, is this a function? Well, if you don't know what this graph looks like, you can always start with the table to see what happens. So let's try plugging in the -2, -1, 0, 1, 2. If we plug in -2, then we're going to get the square root of -5, which does not exist. -1 gives us the square root of -4. 0, the square root of -3. So still we're having numbers that don't exist. Square root of -2, the square root of -1. So what happens if we plug in 3? Then I get 3 minus 3 is 0, so the square root of 0 is 0. If I plug in 4, then I get 4 minus 3 is 1. The square root of 1 is 1. If I plug in 5, I get the square root of 2. So now we have values that are going to show up on our graph. If I graph those, I'm at 3, 0, 4, 1, and 5. Root 2 a little over 1, so it's going to look something like this. Okay, so you can see just half of our graph has been reflected over the line y equals x. Alright, so the question now is this inverse graph a function? Okay, since we are just taking the principal root, so we're only taking the positive answers, then for each x we only get one y value. It does pass the vertical line test, so we can say that yes, the inverse is a function. And again, we can write that as y equals just positive the square root of x minus 3. Okay? So let's look at B. Find the inverse of y equals 10 minus 3x. And let's see if this is a function. So again, we're going to switch our x and our y. So I get x equals 10 minus 3y. I need to solve for y now. So let's move 3y to this side. Move the x over. So I get 3y equals negative x plus 10. Divide everything by 3. So y equals negative 1/3 x plus 10 over 3. So is this going to be a function? Well, yes, we know it's going to be a linear function. Okay, we can graph this function. We know that our y-intercept is at 10 over 3, which is 3 1/3, about here. And our slope is negative 1/3, so we can actually go down 1/3 over 1. Now let's go down 1 over 3. Okay, so this is what our graph is going to look like. Alright, so looking at this inverse function and its original function, let's find first the domain of f of x, just our original function. Well, we can plug in any x value here. There's no restrictions, so our domain is going to be all reals, basically all the values of x that are real, and our range, since this is linear, it's going to keep going in all directions, so range is also going to be all reals. Again, f of negative 1, we know that this is our function is going to be y equals negative 1/3 x plus 10. And again, we could put y here. We could also say f of negative 1 of x. That's saying the inverse function equals negative 1/3 x plus 10 over 3. And again, this keeps going to the left and to the right. So our domain here is also going to be all reals. And our range is our y values, which again, this is linear. It keeps going in both directions, so our range will also be all reals. There's no restrictions here. I could plug in anything for x and get anything for my y. Alrighty, that is all.